Hello, I am Kaito Takahashi from Academia Sinica, and I'll be presenting on this project, Rational Design and Development of High-Performance Catalysts for CO2 Conversion to Valuable Products, which is a joint project of 5 different members. Our first year progress report will be concerning the understanding of CO2 reduction reaction on diatom catalysts. But first, let's mention a little bit about this CO2 reduction reaction. Due to the emission of CO2, the world is facing a lot of crises due to global warming. And one key aspect that we have been working on is to study catalysts for CO2 reduction reaction, CRR, and produce valuable products like methane, methanol, ethanol, and ethylene. The target of our first year study are C2 products. So products with 2 carbons from CO2. Here I'm showing you a schematic of CO2 binding onto the surface, star, and then getting reduced and further reduced to make CO, and this CO could get further reduced here, making COH or CHO on the surface. Another reaction is that CO can react with another CO, or these two COH or CHO can react with CO to make these what we call the C2 reaction intermediates. And after this, the reduction reaction can proceed, and in the end, we can have ethylene or ethanol. It is known that copper 100 surface is more favorable compared to copper 111 surface in making these C2 products. And we believe the CC coupling is the important point. If one looks at this Angevante review paper, we see one important aspect mentioned concerning the rate determining step of this CC coupling forming CO-CO, and that is this coexistence of copper plus and copper 0, oxidation state +1, and 0 copper on the surface to promote reaction of CC coupling. Our system is the atomic doping of transition metals to graphitic carbon nitride. We decided to study doping nickel, manganese into graphitic carbon nitride. Here, carbon is given in gray, nitrogen is given in blue, nickel is orange, and manganese is purple. And this system has been experimentally realized. So there are reports of using this surface. One important aspect we found out looking at our literature search is that some studies have mentioned that this nitrogen can easily desorb and make vacancies. So in this study, we studied not just doping nickel manganese into pristine graphitic carbon nitride, but also putting in nickel manganese into graphitic carbon nitride with this N vacancy. It turns out that this N vacancy doped substrate is a promising catalyst for ethanol production. So we will go in to mention our calculation results. So one question we had is, if we have 2 different metals, can we promote this CC coupling? And how is the electronic state of the 2 metals helping this reaction? So here we are looking at the projected density of states as a function of energy for our doping to pristine and doping to N vacancy graphitic carbon nitride. This is a bit confusing, so we just extract out the local density of states for the nickel and the manganese. Looking at this nickel for both pristine and vacancy graphitic carbon nitride, we can see all the d orbitals are occupied, signifying we have nickel, zero oxidation state, D10 occupation. On the other hand, when you look at the manganese side, we can see only the alpha or the up spin being occupied and beta being mainly unoccupied. Therefore, manganese will take +2 oxidation state with D5 occupation. And if we look at the spin density, as expected, all the up-spin contributions are at the manganese. And since all 5 d orbitals are occupied, the sum is spherical. We also looked at the calculated beta charge and found that nickel manganese, this transition metal, has +1.6, while the N-vacancy graphitic carbon nitride has -1.6. We can think of this as +2 manganese, matching the D5 occupation, 0 for nickel, and 2- for this N-vacancy graphitic carbon nitride. So this is all consistent with the analysis of the density of state. So how does this electronic state help us? Here we are looking at the reaction process of CO2 to form ethanol. And here you can see the schematic geometries. The key point is we only need -0.55 volt limiting potential to form this ethanol. And the important reaction for the CC coupling is between CHO and CO, making this CO-CHO reaction intermediate. We are looking at this reaction more deeply. Here is the initial state, transition state, and the final state. Here I'm presenting a more detailed view of the reaction process. We can see this high barrier of about 0.8 EV is 3, the CC bond formation process. And then at 4, we will have a manganese oxygen binding. And then at 5 and 6, we see that the C1 carbon moves into this bridge site, making a very stable reaction product. We looked at the charge along the reaction path, and here along this reaction path, we separated to moiety 1, the adsorbate, moiety 2, the substrate, and moiety 3, the metal. And what we can see is metal is constantly around 2, while the adsorbate and our N-vacancy graphitic carbon nitride is close to -1. So we can see that the substrate has donated an electron to the adsorbate. Why would donating an electron help? To clarify the effect of the extra electron, we look at the neutral case reaction of CO plus CHO in the gas phase versus if there's an extra electron of CO plus CHO anion. In this case, the heat of reaction is -1.6 eV, much greater than the neutral case. Therefore, in our case, this extra electron from the N-vacancy graphitic carbon nitride promotes the CC coupling reaction. As conclusion, by doping nickel manganese, into this N-vacancy graphitic carbon nitride, we can control the electronic state, and this control of electronic state helps produce ethanol at a low limiting potential with low kinetic barrier. Lastly, here are the outputs from our project, 3 papers published, and 1 outstanding oral presentation award. Thank you for your attention.